Schrödinger's cat, the paradox that shaped quantum mechanics. What does a thought experiment about a cat trapped in a box have to do with quantum physics? Schrödinger's cat is one of the most famous paradoxes in science, highlighting the counterintuitive nature of quantum mechanics. Today, we'll explore this thought experiment, its origins, implications, and why it continues to spark debate among physicists and philosophers. What is Schrödinger's cat? Schrödinger's cat is a thought experiment proposed in 1935 by Austrian physicist Erwin Schrödinger. It was designed to illustrate the strange and seemingly contradictory aspects of quantum mechanics, particularly the principle of superposition. The setup is simple yet bizarre. Imagine a sealed box containing a cat, a radioactive atom, a Geiger counter, and a vial of poison. If the Geiger counter detects radiation from the decay of the radioactive atom, the poison is released, killing the cat. If no decay is detected, the cat remains alive. According to quantum mechanics, until the box is opened and observed, the radioactive atom exists in a superposition of decayed and undecayed states. Consequently, the cat is simultaneously alive and dead. This paradox challenges our classical understanding of reality and raises profound questions about the role of observation in determining the state of a quantum system. The science behind the thought experiment. Schrödinger's cat was conceived to critique the Copenhagen interpretation of quantum mechanics, which states that a quantum system exists in a superposition of states until it is measured. This interpretation, championed by Niels Bohr and Werner Heisenberg, suggests that the act of observation collapses the superposition into a definite state. In the case of Schrödinger's cat, the radioactive atom's quantum state is described by a wave function, which encompasses all possible outcomes, decay or no decay. The cat's fate is entangled with the atom's state, meaning the cat is both alive and dead in a superposition until observed. Schrödinger introduced this scenario to question whether quantum mechanics could be applied to macroscopic systems like a cat, or if its principles were limited to the microscopic world. Key interpretations of the paradox Schrödinger's cat has inspired various interpretations of quantum mechanics, each offering a unique perspective on the nature of reality. Copenhagen interpretation. This suggests that the cat's state is undefined until someone observes it. The act of observation causes the wave function to collapse into a single outcome, alive or dead. Many worlds interpretation. Proposed by Hugh Everett, this interpretation posits that both outcomes occur, but in separate parallel universes. In one universe, the cat is alive. In another, it is dead. There is no wave function collapse, just a branching of realities. Objective collapse theories. These propose that wave functions collapse due to physical processes, independent of observation. For example, large systems like a cat might experience spontaneous collapse, avoiding superposition altogether. Relational interpretation. This view suggests that the cat's state depends on the observer's perspective. For the observer outside the box, the cat is in superposition, but for the cat itself, there is no paradox. Implications of Schrödinger's cat. The thought experiment highlights several key issues in quantum mechanics. The measurement problem. How and why does observation cause the collapse of a quantum system's wave function? This question remains one of the greatest mysteries in physics. Quantum to classical transition. Schrödinger's cat bridges the quantum and classical worlds, raising questions about where the boundary between them lies. Why do we observe definite states in everyday life rather than quantum superpositions? Entanglement. The cat's state is entangled with the atom's state, illustrating how quantum systems can become interconnected in ways that defy classical logic. Philosophical questions. Schrödinger's cat challenges our understanding of reality, truth, and existence. Is the cat truly both alive and dead, or is this merely a limitation of human perception? Real-world applications of the paradox. While Schrödinger's cat is a thought experiment, its principles have practical implications. Quantum computing, qubits, the fundamental units of quantum computers, operate in superposition states, similar to the cat's paradoxical state. This enables quantum computers to perform complex calculations exponentially faster than classical computers. Quantum cryptography. The principles of superposition and entanglement underpin secure communication methods, such as quantum key distribution. Quantum measurement devices. Understanding the role of observation in quantum mechanics has led to advancements in precision measurement and quantum sensing. Schrödinger's cat in popular culture. Schrödinger's cat has transcended physics, becoming a symbol of paradoxes and uncertainty in popular culture. It has been referenced in TV shows, movies, books, and even memes. Its widespread recognition reflects its power as a metaphor for the complexities of modern science. Conclusion: Schrödinger's cat is more than a quirky thought experiment. It is a profound exploration of the nature of reality, observation, and quantum mechanics. It challenges us to rethink the boundaries between the quantum and classical worlds and raises questions that remain at the forefront of scientific inquiry. If you've enjoyed this deep dive into the quantum realm, don't forget to like, comment, and subscribe to our channel. Let's continue exploring the mysteries of the universe together.